Hello everyone, I'm Ilya, co-founder of Near, and I'm joined with Adrian, co-founder of Anoma. We're gonna dive in here into how Anoma works in Not So Sunny Seoul today. So Adrian, take it away.
Thank you very much for having me. Yeah, I'll try my best. This is the first time we're whiteboarding Anoma, so let's see how far we get.
Maybe to start, describe what Anoma is.
Yeah, let's start with a little bit here with the sort of where it comes from and why we ended up building Anoma and thinking about this problem. Back in 2020, everyone was building these VMs, and it seemed to us that really most users don't actually have transactions as in fully balanced things that can be executed against a specific state machine, but rather they have intents. They have partial things. They have a partial state transition. Like I want to trade A for B, you may want to trade B for A. But I don't have anything, sorry, not hitting the mic, so my intent is not directly executable against some ledger because it's not balanced yet, right? And so one of the big problems was how do you actually do decentralized counterparty discovery or distributed counterparty discovery and distributed solving? And really building this on the existing models of transactions is very, very difficult because you don't have the networking infrastructure to, for example, gossip around intents. You don't have flexible network topology here. So this is really the origin idea of Anoma, of allowing people to have intents, which are partial state transitions, that can be combined with others in order to form fully balanced transactions. Maybe one extra important point here is that this model is also, incidentally, turns out way better at information flow control. So when you think like, okay, what does a less revealing world look like around data protection? A lot of data starts living on your device. And the current model of a lot of shared global state means we all have to ship the state into the same place, so that we're revealing it. So once you start having intents, it's way easier to construct also proofs over partial state transitions, so I can prove that I'm allowed to trade, I don't know, A for B. You could be transparently authorizing this with a normal signature. A solver somewhere else can sort of take these two things and combine them. And maybe the third important point here is you also get partial solving, which is kind of cool. So one of the big problems right now is that you always have to solve the entire thing. So solving becomes very centralized, whereas with sort of base layer intents, you have the capability of saying, well, I have A for B, you have B for C. Solver picks it up, goes, well, I can collapse this into A to C. At some point, and I send this off, the solver sends this off as a new intent. And then sort of another person at some point in the future is C for A, and now this is actually solvable. And you maybe start to realize it starts looking a lot like rollups with computational compression. So I think what we just ended up sort of discovering from first principles is that intents are a very good match for lots of the actual activity that's happening on these systems at the moment.
Yeah, so maybe just to give a specific example, right? Usually when you are trading or transacting on chain, you need to be exactly specific about you want to use this exchange or you want to use this smart contract. You want to kind of trust this balance. And it's especially more complex when you're doing it cross-chain and you have need to specify now which bridge, what are the kind of counterparties involved in that. And kind of then the idea of intents is you specifying kind of post-condition in a way, like precondition and post-condition, and you letting somebody else finding this route of how these things should be connected.
Pretty much. I mean, what's really happening in the current world of VMs is that people define computational traces, right?
Larger font.
Oh, larger font. They define computational traces. And this is what people sign over. Like in the case of the EVM, for example, they sign over EVM bytecode, right? And so here a user needs to understand all the individual steps of I'm at state A, then I'm at state A prime, and so on. And sort of their opcodes describe how to transition here. This is very difficult for people to do because they have to know all the intermediary steps. In sort of this IM world, it's very declarative. So you define, I have state A and I want to get state B. And here state A could be, I have near on near, and I want ETH
on base.
On on Ethereum. And actually, in this case, this is just my intent. I just say I'm only satisfied if I take delivery of the asset on Ethereum. I'm sort of giving this up on near, but here I don't care whether it moves via some bridge, and I actually don't even care whether the bridge is insecure, because I don't take bridging risk. Because I should also, I mean, this gets fairly complex in terms of specification, and front ends will have to do some work here. You also need to specify what kind of ETH, like you want native ETH, not like Arbitrum ETH. Right?
So, I mean, you specified on which network, right? So.
Yeah, but that's not necessarily the same, because I assume you also can have Arbitrum ETH on Ethereum.
Bridged back on Ethereum?
Yeah, so like, just for clarity's sake, you have to actually be very specific on what kind of assets you want to take. And so this is sort of from the state model. And the other thing is this doesn't just work for assets. I mean, for assets, this is an obvious example. But this is fully programmatic, so an intent can also say things like, I want to participate in this Gitcoin DAO. And if 500 of us get together, the individual intents never get settled on chain, so we don't have to individually pay for transaction fees to participate in Gitcoin. We can rather combine all 500, run the compute in order to actually figure out what solution, like who's going to get funded, and then just post the end result with the intents as sort of the authentication to this update. Really think of Anoma as being very declarative, or the intent model, or the intent machine, I should actually stick to the name, the intent machine being very declarative, as in only specifying state changes, and the system around it just being built up in order to allow for these state changes to happen.
So you pretty much invented Haskell of blockchain.
It's not exactly Haskell.
I know, I'm just joking.
But there's a point. We advance with programming languages towards declarative models and functional languages. I think it's probably fair to say there's some, but the blockchain is not built in Haskell. It's very important. No blockchain in Haskell works, I think.
Okay, so yeah, so I think like from what you're trying to solve, this makes sense, right? Provides a different way of interfacing with not just one blockchain, but kind of every chain in a way, and fits really well with chain abstraction. And it provides kind of this framework that is pretty general. So let's dive in how it works.
Yeah, actually, here the important thing is the intent machine really is a developer and user abstraction. Mm-hmm. It's an interface. It's not an intermediary. It's not there's like an intent blockchain you must send all your intents to for them to work. It's any chain that has an intent adapter can just use it. So you can retrofit, or you can build an intent machine on Ethereum, you can build it on Near, and a lot of the, actually all of the P2P gossip infrastructure for the intent gossip and solving component is completely chain agnostic. That's just within the intent framework. Mm-hmm. There is some advances here that we've made in terms of virtual machines. You can build virtual machines that are specifically tailored to sort of accept these kind of state updates, and there are advantages there, and we can go into them later.
Okay.
Yes, where do you want to start?
Well, let's start with, you're saying pretty much, overall high architecture. So it sounds like there's adapters that live on every chain. There's gossip infrastructure. There's kind of
how do you split this best?
Some way to submit all this.
So it all starts with a P2P gossip stack. And just as a side note, not enough people in blockchains worry about gossip. We spend a lot of time on other things. We should spend way more time on action networking because this is a really difficult problem. And so in Anoma, there is one unified Anoma gossip network effectively. And this may have many different nodes. And nodes can have different capabilities. So we don't have the same abstraction that exists in, for example, Solana, where you have a bigger font. Full node, that gets talked to via some RPC, right? This is not the model here. So we don't have this abstraction boundary. Nodes can run the entire software or the entire capability stack, or they can choose which kind of capabilities they want. So for example, this could be Ilya's phone, and Ilya's phone only wants to participate in very limited intent gossiping. Pretty much you just want to be able to send your own intents, and maybe if you're actually into trading, you also want to like subscribe to a super small subset of intents that float around the network. But then we can also have like a Figment validator node for the Anoma-based chain and the Ethereum-based chain. And so like different nodes can have different capabilities, and importantly, they can also live in different trust zones. Actually, we have different markers here. Right, like
actually switch.
Oh,
Given you're left-handed, so.
Oh yeah, that's a good point. So you can have like different trust zones that are maybe overlapping, but maybe not necessarily overlapping, right? And so different trust zones are what people would historically call different blockchains. But what I really mean here is you have different trust assumptions. They may be proof of stake, they may be proof of authority, they may be single node chains run by a government, who cares? But so all these things can sit on a connected, sparsely connected P2P stack. And so when I send an intent, for example, from my phone, I can either sort of do flood all, and then anyone that's interested can actually receive this intent. I can also do more interesting things where, like, let's say I want to trade BTC for ETH, and I actually want to do decentralized counterparty discovery. I can even do this sort of like reach out to who has, I don't flood everyone, I only flood like 2 people first. And if they can actually satisfy this intent, then I don't have to reveal my intent to everyone. I think from an information flow control perspective, it's very important to understand that if you want to get counterparty discovery, you must reveal something. I can't go, I want to trade this closed box, please like solve this for me. This doesn't really work. So you always need to reveal some amount of state that you're willing to trade. And here you can, in this kind of networking model, you can actually decide what kind of state you want to reveal and to whom. Yeah, and here, effectively, other chains can be run via a sidecar. So you can have like an Anoma network and then a Near network and an Ethereum network, but they're still globally connected via this P2P gossip stack. Maybe the other cool thing is you can actually attach fees for intents. So intents are just arbitrary, but you can say, well, I am willing to put, I don't know, a 0.5 USD fee on this intent. If this node cannot actually solve this intent, it could rewrap this and say, well, I'm taking 0.1, the next person gets 0.4. If this person can actually settle it, that node still gets a 0.1, and this node gets a 0.4.
So you have some incentive from
yeah. But it's yeah, I'm careful with using the word incentives because everyone nowadays seems to think points.
Oh, there should be points. Come on.
That's true. No, but it's like incentives not at the architectural level, but rather the topology level of like the user behavior level. Yeah. We spent a bunch of time trying to sort of separate what is the actual architecture of the system versus what is the topology of the system, because the architecture is something you can write down. The topology is defined by the market, effectively. And you can take the same architecture and deploy it on a different topology. And this is also,
So maybe like practically speaking, right? So I mean, this is some piece of code that connects how our peers discovered what is the how is this information propagated around trust zones, and how you're saying like I can send it to specific nodes. How do I know like that these nodes are doing this function?
So all nodes are not addressed by IP addresses, but rather by cryptographic identities. And nodes will have to advertise their own capability stack. This will happen also on the P2P layer. But of course, all nodes can effectively like advertise that they support all capabilities. If they actually don't, then you need to like at some point start having local metric here where it's like, I keep sending things to this guy, but he doesn't do anything with them. Maybe I should like downrank them in my local metric.
So yeah, so do you have kind of reputation system?
Yes,
overlaid
but
over
it is mostly local. It is not sort of like what people think of. There's a global reputation system that everyone follows. It's a local reputation system where my node decides this is a good peer or that isn't a good peer. There is some interesting things you can do though, where especially with solvers. So intents come without guardrails, and so we're jumping a little bit here. But if you want to trade a shitty limit order, for example, as an intent, you can.
You can. Yes.
There's nothing preventing you from doing this, and you will get filled, right? So there are no guardrails here around intents. Intents are just arbitrary state changes that you've authorized. If you authorize garbage state changes, you will get filled. But so an interesting question becomes, can we build solver trust metrics where, for example, solvers may still get like shitty limit orders, but they decide to return the surplus value back to the users. And there is a system to track this on-chain where effectively maybe my node eventually also listens to this like on-chain data storage on like, oh, these are like the top 20 solvers that I actually trust a lot because historically they've like not fucked other users, even though they could have. And maybe then a lot of the defaults become that we start having these on-chain trust metrics. Let's see. This is again like more of a topology question,
Yeah,
like
it's
what
like optimization.
yeah, where the market ends up moving. But I think sort of long term it's the right call because it makes individual lives easier effectively.
And so, okay, so for the P2P itself, I mean, what are you using for kind of peer discovery and underlying? I'm assuming not libp2p.
We're not using libp2p. It is a custom hand-rolled protocol on Erlang effectively for P2P discovery. There's not that much to it. These guys form point-to-point connectivity. I'd actually have to look up exactly which routing algorithm we end up using. I don't know off by heart. But this is roughly, so all of Anoma is built in Elixir. Don't hate me. Elixir is a very good choice, in my opinion. I will defend this in public. So we're using a lot of the underlying stack there.
Yeah, I mean, the main challenge has always been around P2P stacks is that Eclipse attacks are pretty easy to do, given you don't have any kind of Sybil resistance. And so
the nice thing is, at least some operators in the network can be staked. For example, the validators in the network have clear cryptographic identities that are staked. There are some thoughts around, even if you have like a lower capability node, let's call it a solver or a gossip node, you could still require them to be staked if you wanted to.
so when you say stake, they stake in Anoma?
Technically, they could be staking any asset, but yes, so the initial implementation stakes XAN or Anoma tokens to effectively provide you this trust metric and the anti-Sybil or the Sybil resistant mechanism.
And they're staking on the base chain, Anoma base chain?
Yes.
Okay, got it. So there is an Anoma base chain.
There is an Anoma base chain. Yes, there is. We can sort of think of, I guess, this blue one as the Anoma base chain. There is an Anoma base chain. But the important thing to realize is you never have to use Anoma tokens or the Anoma base chain if you just want to settle somewhere else. You can send intents and just get them settled in a completely different zone. I think this, Chris wrote about this, interfaces not intermediaries, and I think it's a very important concept that intermediaries are people that are actors on the network that can charge fees, extract rent, that potentially worsen your security model, right? Most modern bridges are currently intermediaries because they're effectively 2 or 3 multi-sig that like ships data around. It's a little bit scary. But on the other hand, you have interfaces which are just protocol abstractions. TCP/IP is an interface. Everyone gets to use it. You can connect to other people over TCP/IP. IBC is a good example actually of an interface too. And I think this is sort of, no one really understood this for the longest time. You can just use IBC without using Atom. It's just a definition of how you do interoperability. And sort of the Anoma intent machine is very similar to this. It's just an interface. It's not an intermediary in the system that is capable of extracting rent.
Yeah, it's pretty much like if you define this pretty much this message in this format, you can send it, and then somebody will try to solve it.
Yeah.
Yeah. Okay. Makes sense. So, I mean, maybe I'm actually curious on the format of the intent itself, like kind of from a structural perspective. Like what things I can specify as like a fully Turing complete?
It is fully Turing
complete.
Is
it in Erlang?
No.
Is it in Haskell?
No. This is. I think this hasn't changed recently. We were using for the transparent execution a simplified version of the Urban Virtual Machine. Okay. Because it's a very small language, it's very well standardized, and it's potential to compile to ZK circuits quite easily. So what you can specify in an intent is, think of this as pre and post conditions. So you currently have some state, and you also specify your sort of outgoing state. And then you also have effectively a program attached to this. And a program can do arbitrary things. So you can do things like if weather in Seoul is bad, buy Bitcoin, right? So you can do these very programmatic things over the specific state updates to sort of condition them on at what point are they actually allowed to happen or not.
Wait, is it buy Bitcoin or get me state B?
Effectively, yeah, this is actually maybe like confusing written. It's I have some state. This is fixed by sort of the system state, right? I can say I am willing to accept either state B or I guess state C, depending on the weather outcomes in Seoul. This, of course, and here it's important to understand again, just submitting an intent does not give you settlement guarantees. If you try to buy something that no one else is willing to sell, you're not going to get the thing, right? Like intents don't mean, and this is the important difference, like when you have a balanced transaction, you can update the system state. Just because you have an idea for an intent does not mean you can update the system state necessarily. You need to find a counterparty that's sort of willing to interact with you here. And for example, here you can also do things like, which I think is actually very important. I only want to interact with the counterparty that's not on my local block list. For example, if I'm in Switzerland, I should like adhere to Swiss sanctions law, right? Because I'm locally in Switzerland, I should adopt Swiss sanctions. This is currently impossible to do in the space because someone lives, I don't know, in Zimbabwe, but they're still like effectively bound by circled US sanctions, not by their local enforcement. And so with Anoma, you just make this more flexible where everyone can decide what kind of restrictions they want to place on counterparties. For example, you can also say, I only want to interact with counterparties that are on my whitelist.
So just so I'm assuming there's a signature somewhere here.
Yeah.
Which this signature, like, so when we talk about the state A, let's use a specific example, right? Let's say I have some near tokens for simplicity. So is this signature, like, what does a signature authorize pretty much, right? Because I'm assuming like I say, okay, here's 10 near.
It authorizes the willingness to sort of spend this.
Yeah.
But in exchange for something that satisfies this program condition.
Yeah. So when I create this, right, and I gossip it to other nodes, right, like it didn't actually withdraw my near yet.
No. Right. This is a good point actually. You can issue as many intents as you want.
Yeah.
They're free.
Okay.
Like at some point, your peers may limit you because you keep spamming them. That's a very well-established problem in like Web 2. We can solve this mostly. But so you can issue an arbitrary amount of intents, and just when they get executed in the specific trust domain that you want them to be executed or that they need to be executed in, do they actually get executed, and the near gets taken from your account.
Okay, so let's get there. All right, so yeah, so this is just like, here's what I'm willing to spend. This is kind of result I want to receive, which indeed can be programmatic. This is written in Urbit VM.
We've tried Wasm. Wasm sucks.
Wasn't great. Separate conversation. All right, then you said also you're specifying some additional like kind of broadcasting.
That's not specified in the intent necessarily.
It's not intent. Okay, so this is just a wrapper around messaging, like networking.
This is just the sort of who you're willing to broadcast this to is just
But you do need to like lock it. I mean, kind of spend it here as well, right? When you're actually settling it.
No. So like just intents don't give you double spend protection. This only happens actually at the settlement and ordering side of things. So for example, you could send the same intent to 3 different peers.
Yeah, they all try to solve it at once.
They try to solve it, and whoever gets there first gets there first.
Okay. Yeah, so that's pretty very important note. Then, and so here you may have like a white list or black list. So is this just part of the program?
It's all part of the program. There are no special fields here. There's really, you have this executable, which should be very small because it ideally, for simple things, you ideally don't need it. Because this costs gas in the end, so it like makes your things more expensive. You can just say, I have state A and I want state B. That's way easier because then you just like effectively write like a state layout here. Like I'm at state A, and I'm willing to hold these keys under like in the Merkle tree in state B. And then you just sign over this, and then what the actual implementation checks is that so you then take multiple intents. You take like I1 and I2 into a single transaction. You execute them, and then I1 checks whether the sort of proposed resulting state of this transaction is compatible with its state B. Right, so like imagine a solver takes intent 1 and intent 2.
Well, I mean, let's wait a minute. So what is the format of this?
Again, this could be like, I don't know, what's the conversion rate? I don't know, let's get 1 ETH or something like this.
Oh, sure. But like how are you specifying this? Like this address, 0, like, because this is like, I'm saying root.near is willing to spend 10 near, but here you need to specify
this address holds
XYZ holds
10 ETH, or 1 ETH.
1 ETH, but let's say this address already holds 1 ETH.
Then you'd have to specify holds
incremental
effective, yeah.
Okay.
This depends a lot on the specific state layout that's enforced by the Anoma adapter.
Yeah, so that's why it's, because like, let's say, okay, it should hold 2 ETH because I already have 1 ETH, but then somebody already settled this once, and somebody's trying to settle it again. So
yes, in that
like
case,
the state is already.
You also want the counter in this case in order to deconflict this, I think.
So is there like a nonce, like pretty much you're specifying here nonce on the account?
Effectively, like if you have this model where you want to do incremental things, you'd also have to have a nonce in order to prevent this kind of thing that you update a sort of incremental number.
But this is because it's not going to be submitted from this account, so it's not this account's nonce. Is there like a?
I know this is sort of in the sort of
nonce.
state layout for in the intent. You'd have to say that this account, it's okay if this account holds 1 ETH. Actually, wait, we're doing this in the sense that we just look at the transaction output. So you'd actually. Ideally, the state on chain doesn't matter. It should matter like what is the output of this transaction. Okay. I have to say this gets a little bit tricky in terms of building the Ethereum adapters because the state layout doesn't work well for this. In Anoma, in the Anoma virtual machine, you would literally just say, because it's a resource machine, it's not an account model or UTXO model, but you sort of create. You consume these resources and create new resources. So
I mean,
the
the
output.
UTXO, I understand. Yeah, you're saying I want a new UTXO which is
Effectively,
this, but owned by my key.
Yeah. So you have to emulate this on sort of Ethereum, for example.
So your Anoma adapter pretty much is like a internal UTXO model.
Also, Anoma is not a UTXO model. It's more like a resource model because UTXs, it's like UTXs but with full programmability like accounts.
Sure.
Yeah. The problem is like when you tell people Anoma is a UTXO model, everyone is very confused about how Anoma works at that point.
Okay.
Because it's like not a UTXO model in that sense. But yeah, this is roughly the intuition where I sign over a specific sort of origin state and I define what my end state is, and I also, actually the signature is over both here. Right, you have a sig over both. That's the program.
Mm-hmm. Well, that's why. Yeah. Okay. And so program will be also executed when this is pretty much settling. Okay, so yeah, let's actually like go through an adapter, like okay, received, solved, intent. What's happening?
Okay. Let's see if we can whiteboard this. Okay, so let me see, where do we start here? We're going to start with a very simple. So you have sort of beginning state, which is, I guess, like.
And so Anoma base chain is presumably like
heavily optimized.
It's heavily optimized for just settling intent.
Yes.
Like, solutions.
Essentially, yes. This is like the Anoma execution. I was talking about this yesterday, 2 days ago. The Anoma resource machine, which is really similar to the near VM or the SVM or the EVM, is just it unbundles the state layout from the instruction set from sort of the message passing model. So the Anoma resource machine really just cares about the state layout, and it just cares like this transaction modifies these state keys and is the intent okay with signing over these state keys? And so you have to build an implementation, like an adapter is effectively an implementation of the Anoma resource machine on other systems.
Yeah, so just for simplicity, for me to understand, so there's some address XYZ, and then it has a set of resources like, Anoma token, Adrian token, touch token, with, X, like 10, 5, 1.
Yep.
And like this is just unbound, like compared to, for example, EVM, which has this inside ERC20s, like each one of these is like a separate contract. It's inside some state trie of that contract. And so like specifying condition on that is complicated. You just have this kind of, or do you have more like an object? So there's an object with like a unique ID that has an owner.
Like this would be the object effectively.
All of the resources for the owner.
So like my owner is effectively this is the object, and I transition this to a new object.
Okay, yeah.
When I want to spend.
Yeah. I mean, because the alternative is what, for example, Sui is doing, which is each token or each NFT is a separate object which has an owner, and you can change the owner.
So the other thing, tokens are also represented as these kind of objects. So you still have like a 0x, I don't know, BTC key space, where, because this doesn't, it also includes it, so like
a program.
You can't go under 0, for example, right? Like, or you can't mint more than was brought in via some bridge. So you can have more logic in these objects too.
Yeah, so there's a program attached to the object,
so here you then define, well, I'm willing to, so my beginning state is this, and I am willing to be at an end state where I hold 0 near, if and only if I hold, I don't know, 1 ETH. And then sort of a solver would take also the inverse to this, if there exists such a thing, combine this into I1, I2, run this locally effectively, because the compute doesn't happen on chain. So the solver runs this locally, gets then a transaction candidate, or like a T1 or T prime. And the T prime just contains all the sort of proposed state, and then the proposed state is again fed into this intent, and you check, does the intent return true when executed against this proposed state?
All right, let's walk through this. All right, so this is, you're saying there's two intents, like for example, somebody else wants to sell.
Yeah, it's this one, effectively. This is, so intent I is 10 near.
10 near for 1 ETH, and then there is 1 ETH
for 10 years.
For 10 years. So this is pretty much for example, I'm a market maker, and so I run a solver, and I'm willing to make this trade, so I'm gonna like attach this. Yeah. Okay, just for simplicity. And so I create this, so what this looks like is 0 near on this 0xa, and 0xb, which is a market maker, now has 10 near, and
this also has 1 ETH, right?
Yeah, 1 ETH, and this,
And
now this has 0 ETH, for example. So this is the transaction candidate.
Exactly. With state keys updated. With
some proofs pretty much toward state.
Yes, and this is actually the cool thing. This maybe is, so intents may either be authorized with like plain text, like we just have an authorization field. It's not a signature. It may be a signature. Like if you use plain text signature, sure. It could also be a zero knowledge proof that you own some resource in the tree. So there's just an authorization attached, which also has to verify to true.
Okay, so
but in a simple case,
this transaction includes two authorization.
So yes, it includes the two intents effectively as authorizations for these things.
Oh, so intents are included here, right?
Yeah. And then it also includes an actual signature by the solver to pay for execution cost.
Okay.
And so, for example, you can also do something here where you include an extra, maybe you actually only want to trade, like you're willing to spend 9, and you're willing to trade 9, but you're willing to spend 1 near
on the fee
as the fee, which are only claimable upon settlement.
But is this you specifying this as intent, or you're just saying I want 10 for 1 ETH, and the solver should like attach that there is the 1 for 9, and then there is 1 near that comes to their account?
You can do this both ways. You can also can trade shitty limit prices and do this implicitly.
Yeah.
Or you can trade specific prices and just attach a sort of a claimable output. Just that anyone that settles it is spendable to whoever submits this on chain. If the rest is balanced, right?
Yeah.
Not just I submit this intent on chain and I get 1 near. That'd be problematic.
Okay, so then this bundle goes on chain. Your blockchain kind of verifies that this outcome state matches this intents, and first verifies that solver has enough to pay for transaction fees, verifies this outcome state matches intents, and applies this outcome state to the chain. So you don't actually have any execution on chain, you just update the state.
Yes, it's like the right model. Blockchains were designed for verification, not compute. We just ended up building systems that compute the colors of NFTs on chain and smart contracts, and
it's great.
Everyone wonders why this is super expensive and inefficient. And maybe the other important thing is, so like on chain you clearly do double spend checks. Right, like this proposed thing still needs to be consistent with the chain history or the chain state.
So how will you verify this in this case?
Like you'd have to check, does this account actually have 10 years to spend, right? So like this account can't be negative in negative.
But I guess like how you do it in a generic case, it's not about fungible tokens.
As in, does this account hold that state key, and is this account the owner of the state key effectively?
Okay.
Like think of states really as very arbitrary things. On like it may be a token, it may be something else, and we just check on chain. You just check: is this account allowed to modify this state space? And then in this case, you'd also for the token, you'd also involve sort of the token contract the token resource to make sure that the token doesn't go negative and that this person actually has access rights to the token. I feel like there's a question bubbling.
Yeah, I'm just in my head trying to execute an intent. So, no, it's just so you. I mean, here it says like, okay, 10 year going to be spent, right?
Yeah.
So you check, okay, 10 year. You have 10 year to spend. This is okay. So my question is, let's say I had two intents. I had 20 year. I had two intents in parallel for each one for 10 year. So like I want both. Both solvers did this at the same time. They put that there should be 10 year left, right after their 10 year.
The second thing will fail.
Okay, got it.
This is the simple answer. If it's inconsistent with state history, it will fail.
Okay, got it. So they'll need to like re-execute it, for example, and
which is actually a very difficult problem to solve in a decentralized way. On how do you not waste a bunch of compute cycles on many different solvers trying to do exactly the same thing. But this is really not a question of the architecture, it's a question of the topology of the network. On like, there's probably a point that all fungible token traits go to the same solver. If we can like opt out of the solver immediately if we don't like the solver. Actually, I think what will happen long term, and I mean really long term, is that latency matters. And so like we should pick the solver. If we're in Seoul, we should pick the solver in Seoul because they can give us way better latency guarantees than going to a solver in New York.
okay. So yeah, I mean that's just like who do you route your intents, and then like you can kind of optimize, but you can also just flood it and.
Honestly, if you don't care, you should flood it. This is like the trivial answer, which is essentially this is what kind mempos do. You sort of like, don't care. Fuck it.
Care. But somebody will figure out how to put the block.
Exactly. I think it's so to a large extent. Anoma just provides an actual architectural and spec'd out version of a lot of the systems that are starting to appear right now. Where right now we just all go, we should all send our
transactions to
everyone, and Justin Drake runs a major relay, which is fine, right? But like it's a very ad hoc kind of thing where Anoma just provides sort of a architectural description of the entire system and how other people can opt into this, how you can easily switch between people. It doesn't rely on having to, like we all hard code a single IP address into our configs, which is really currently the case.
So, I mean, from perspective of MEV style, like front running and things like that, right? I mean, you're specifying what you want at the end, so kind of you're fine with whatever.
It depends which MEV camp you're sitting in, right? So to me, I will give you my definition of what I would consider MEV versus non-MEV. If there's information asymmetry, it's MEV.
Yeah.
As in, if I specify I am willing to trade some asset for some other asset, and I don't trade on a fixed price, and someone else sort of sees this, front runs this, and now I get a worse price, that's clearly MEV. If there's an arbitrage opportunity between New York and London, that is not MEV. This is just geographic arbitrage. This will exist all the time. So Anoma doesn't solve for geographic arbitrage. But Anoma does solve for this MEV where you get front run because you didn't specify your end state, you specified your computational trace. Because, right, like if you interleave different execution traces, you may end up different results. One-on-one CS effectively.
But here you cannot specify like, I want whatever market price is for this. You need to like specify some price, pretty much.
If you want specific market prices, this needs to be encoded at sort of the application layer. Like applications built on top of this intent machine can provide extra guarantees to the user. So actually we can, like one cool thing is that So from an application perspective, so when you think of an app on the IM, the app can include guardrails. So for example, you can say things, I am willing, you only make this spendable to, we have something called, we have threshold encryption, decryption within the base chain, so you can sort of submit an encrypted intent. This just gets ordered. It gets ordered on chain. The chain enforces some amount of batching effectively, where it says, well, or the application can enforce, my batch should be every 15 seconds, and after 15 seconds or 3 blocks, the validators are jointly decrypt all these intents. Now we have a bunch of decrypted intents that are specific to this application. Now solvers can go, we have all these decrypted intents, let me actually compute a solution to them, submit them to the app, and the app can sort of pick the optimal criteria. This is kind of, it's similar to CowSwap, but instead of relying on a central solver or central server to pick the best solution, you can do this on chain here.
But like the solver need to respect this order?
There's no order here. This is just, the solver needs to respect the batch. Sorry, this is like, I should not call this batch because they're ordered because they're not ordered. They're batch. They're just encrypted byte strings, right? And we just agree all these encrypted byte strings belong to this batch.
And so when, as a solver, I find, like, I cannot split and like, I'll solve just 1 in 10.
Exactly.
And front run everything else?
Exactly. Okay. This is sort of the optimality criteria you can enforce within the application on chain to say, I
want all those things to come together.
All these things must come together. Maybe you're allowed to include external liquidity sources. Maybe you don't. This is really sort of on the application side. But yeah, it's important to understand, like intents at the base layer don't provide you any guarantees. If you do market orders, you will get fucked. This is just, unless you're like, you already spoke about this kind of trust metric. You can maybe, but this is not a guarantee. Maybe you can build economic guarantees there, but it's not a sort of...
Well, I mean, pretty much what you're saying, like the reality is right now, actually, Uniswap is not a market order. Uniswap is actually a limit order with, like, hopefully it will be better than that. Because what you're saying is you have a price, like the current one, but actually you have a limit order of you will not take anything below that.
Yeah.
So you're just fine with everything above it, but...
That's true, actually.
So it's just like, it's not already the market order.
Yeah.
Just, you hope that nobody will front run.
Yeah, it's just a very wide limit order effect.
Well, it's 0.5, right? Slippage, right? Or,
that's pretty wide.
It is pretty wide, but you can reduce it. Depends on liquidity of the thing. So that's why I always like, why doesn't Uniswap just return that? Whatever you specify as min amount, it just return that.
Yeah.
And now there's no more MEV, and Uniswap LP actually earn more money.
Lots of money.
And now all the front ends can just reduce that percentage based on the volatility of the asset.
Oh, that's actually interesting. I haven't thought about that. That's an interesting thought, actually.
Yeah,
just make them like strict limit orders.
Yeah, solving MEV one app at a time.
Yeah.
All right. This makes sense. You have threshold signatures to pretty much have some, well, not ordering, but batching.
Yeah.
Okay, so this is how it works on Anoma base chain. Now, how does it work on account-based model?
So this is honestly harder. Because you effectively, all these things are Turing complete.
Yeah.
But as a result, you then have to emulate the Anoma resource machine. So the Anoma resource machine is also a circuit, so you can technically construct a rollup proof of the correct execution of the resource machine. So like the way this would work, if you have like, this is not a fixed name. I'm calling them APAs, the Anoma protocol adapters. I don't know if that's a good name, but it's the shortest acronym I could come up with. So if you want to emulate full Anoma, like the full Anoma resource machine directly in Solidity, you may run into some gas problems, let's say it this way. So this will, for most systems, look like effectively a ZK proof. over a valid state transition of the Anoma resource machine.
So this will require somebody to deposit first into adapter what they're planning to spend.
Yes. In the first step, this does require effectively assets to flow into the adapter, so be under the control of the adapter. Long term, there's something with Typhon and Chimera chains where maybe actually we can have validators guarantee sort of that assets can move on a single block and you don't have to lock them. Think of this as shared sequencing where maybe if there's enough, so we can actually also go into Typhon, which is a consensus of Anoma, which is heterogeneous narwhal plus heterogeneous Paxos. So here I had this topology model, right? And like different security zones may have different overlaps. And so if you have a large enough overlap between two systems, this is like a chain, so this node is on both chains, right? So if you have enough overlap in the validator set can start offering atomic execution as well as synchronicity guarantees for a single block. And the way this works in Typhon, very high level, you have like chain A, chain B. You can split your state into effectively partitions. And this is like the state B partition. And chain B does the same thing, has a state A partition. And then here in the middle, you can form a block that is synchronous with regards to both partitions effectively. Yeah, this is chain A. This is why this is.
What do you mean? What are you calling partitions here?
So this is one chain. And within the chain, you can split your state space.
Okay.
And you effectively say that
part of state space, I
want to be able to have in a Chimera chain with this other chain.
Okay.
And if the other chain does the same thing, and there's a large enough overlap in the validator set, the validators can effectively run a new process that just creates blocks over the shared state space, because they also guarantee that you can't move out of the state space without this being cleared here.
So, okay. So
it's actually probably somewhat similar to Nightshade now that I think about it.
Yeah, it is in a sense, but well, but like for this chains are like needs to have your consensus.
They need to have Typhon consensus.
Typhon consensus. Okay, so it's not like you can
Again,
grab
like,
BTC and just say like, hey.
Again, there are like
let's share sequence stuff.
As long as you have fast finality, this should work across many chains, even if they don't have by effectively running smaller sidecars. So like if you can run a sidecar.
But like I mean, so okay, well you're producing a block, right? And let's say it was BFT consensus. So like you will say that if this is a shared block across two chains, I mean in a way, let's draw it like this. And the next block is already, but like they only can touch the state that is shared.
Yeah.
And so like there's some validator who is in both groups who says like, you know guys, what? I'll produce a shared block and I'll just ignore every other transaction that's not touching shared space.
Yeah. Pretty much. And so this gets faster the larger the overlap is between the validators.
If you have like all validators overlap, they just merge chains.
Yeah. But the nice thing is they don't have to. I mean, like, for example, you could have like exactly the same logical validators. It's like Figma and Chorus 1, just two validators in the world, but they have a data center in Asia and a data center in North America. They could run two chains at the same time and only merge them when people are actually willing to pay for the extra latency between North America and Asia. If that makes sense.
No, I understand. Yeah, they don't need to produce this merge block if there's no transactions, for example, in this merge state. I'm just specifically is like this merge state means like all other transactions are not included here.
All other transactions that could influence this merged state are not included. Yeah. Okay. I mean, you can have like again, like this is the problem I think with the existing designs. It's like our state space layouts kind of suck. And I mean, I like ERC20s, but the fact that all ERC, like that a single ERC20, all balances live in the same global mutable state, makes some of these things harder.
Yes, very hard.
So it's like, this is an attempt to kind of resolve this so you can move parts of your state into it without affecting all, like, ideally you want to structure your contract so that you have lots of local state, not lots of mutable global state. Oh wow, 40 minutes, no, 50 minutes already. I think we need to do like another 3 hours. Let me see what else is interesting here. We spoke about the intents, we spoke about consensus a bit, we spoke about the gossip stack, we spoke a little bit about the Anoma resource machine. I think sort of just from, I don't know if you want to touch a little bit upon sort of information flow control concerns here and how you kind of need these systems to offer like reasonable privacy guarantees to users.
Sure.
Because I think this is something that actually most people just don't understand around the idea that so currently all systems are constructed around shared mutable global state, right? So we all have this thing living in the middle. And we all just shared global mutable state. And we all modify this thing.
Sounds like a casino. SGMS.
It practically is, right? So we all modify the state all the time. This has both concurrency problems as well as sort of information flow control problems. With intents, we stop having a lot of this shared mutable state because I have intent A, or intent I, and intent 2 prime, and actually get like a transaction candidate that contains both. So imagine this is like 50, I can do a bunch of netting. I don't have to do all the intermediate computations. I just like net out all these intents because they may touch a bunch of things. So I get a very compact thing that much quicker
Just updates the state,
that just updates the net results of the state. In common lingo, this is called a rollup. With intents, you effectively just get rollups for free to a large extent, or at least you get an architecture that's uniform across many different rollups if you want.
Application-specific rollup. This is a state-specific rollup.
Oh, you're calling this a state-specific. I like it.
Yeah, I mean, I've been trying to talk about application-specific rollups is because right now, when you start a rollup, you start a whole VM with all of the address space, which is not what you want. You want users to have shared address space, and then applications to have their own set of execution and kind of capacity. And so that's where, like I call it, applications is like when your address space still lives on, let's say, L1, but your execution kind of is for your specific application is in a rollup. But you kind of doing this more on the state side. So
yes, Anoma is very state focused. Because I think this is.
I mean, the specific example we have orderly, which runs an order book off chain and then just settles all the trades.
Interesting.
Which is actually very similar to yours. It just nets out and puts the balances, but result proofs will also limit orders.
For orderly, I think it'd be cool to try out the gossip stack because I assume currently orderly is like someone runs a single server. Not a great model. I mean, it's like we can do this right now, but I feel like we need models that like where we don't have a single IP address control.
I mean, I agree.
A bunch of order books.
Yes.
This is like a lot what the
gossip
I was saying
stack,
that like the space needs to think way more about gossip because it's a very difficult problem.
Well, I mean, the question there is always like, okay, well, I mean, as we discussed, like this doesn't guarantee any ordering. So if somebody like, sits on your intent for a while, right? Like, okay, well, now you need to flood it. Okay, now you're actually sending it to everyone.
Anyway. But so I wanted to chat a little bit about privacy. So one of the information flow control here. One of the important things becomes in an intent-centric model, or like if you want to have some amount of information flow control, state needs to migrate to the edge of the network, right? So we don't have this shared global mutable state. Everyone has their own like personal state. And if you want to actually allow these people to maintain their personal state without revealing it to the public, we need a different model where they don't actually submit their entire state updates to on-chain. So what Anoma does here is it allows users to attach ZK proofs instead of revealing that they own some resource within the Anoma resource machine, instead of revealing the entire resource. So they can sort of show, I own 10 ETH without actually revealing which address they own those 10 ETH at. Rather, it's a zero-knowledge proof where that attests to the fact that they own 10 ETH and that they can transition those resources to someone else. So, for example, if I wanted to sell 10 ETH for 100 NEAR, I think this conversion is off, but anyway. Instead of showing I own this at address XYZ, I attach a ZK proof that I own this at address XYZ, or that I own this.
I own it, yeah.
And I'm capable of spending this. And here's also, and anyone that sort of settles this can claim this node, right? Because these are fundamentally nodes in the Merkle tree. And so whoever settles this, whoever takes the inverse, can then claim this node. And claim here doesn't mean interactive, it just means they then become the owner of the node. But I think this is really important to understand because it's very difficult to build.
So, but this becomes then like a UTXO of this ZK proofs, right? In a way.
Pretty much. We like
resource of ZK.
No, for ZK proofs, everything looks very much like a UTXO model. There's no way around this.
Yeah.
But this is like whenever people tell me that they're like, oh, we're going to build like private Uniswap on some VM, I'm pretty skeptical because the entire system is designed around the shared global immutable state.
You need a
this is going to be really fucking difficult to build this as a like within the system.
Yeah.
And I think this is sort of why this move from VM to IAM, not in the sense of replacing the virtual machines, but in terms of
moving away
allowing a higher level of abstraction for developers and users is kind of going to be required because it's going to be very difficult to build a lot of the things that most people really will want on top of VMs directly if you don't have this layer of abstraction in terms of the state layout.
So, but like practically speaking, I mean, you need to first deposit this into a ZK proof, into something that like now is not controlled by you, but you have a
the nice thing
ZK
is
proof of.
In the Anoma state model, it all lives in the same Merkle tree.
So yeah, how is your state actually organized?
How is the state organized? Many Merkle trees, some of which are, so effectively the entire system is circuit friendly. So there are resources, and you can think of this as sort of a tree here. And there are many different resources in this tree. Resources have owners and programs attached to them, or like they're just like these resources here. And
so
then
there's like an owner field.
Yeah.
And code.
And state.
And state.
Yeah.
And state just bytes?
Yeah.
Okay.
Yeah, it's just Merkle. It's just points to key space, so it's just bytes, yeah. And so if you want to spend this, you destroy this, and then you recreate this again here. You don't update them, which is how then you can choose sort of whether you want to include a plain text signature that you're the owner of this thing, or you want to include a ZK proof that you actually own this thing within the tree.
So, but then, like, let's say I executed this order. How does everybody else know that this is destroyed and there's a new owner?
You reveal the nullifier. Like this thing ends up revealing the nullifier. I have to say I'm not a cryptographer, so I am not the best at explaining this exactly. I can send you the blog post.
Okay. So pretty much, okay. I mean, this is like the usual ZK proof UTXO tree.
Yeah.
So you add a new node here, and then
And you have the nullifier tree.
Yeah. And
here
so you check,
cross it out. Nullifier is now revealed.
Okay, got it.
Yeah. Let me see. But yes, actually, this is the other thing I'm skeptical on. Like everyone that wants to build like privacy preserving things without intents, I think it's going to have a really difficult time because intents allow you to move state to the edge of the network. Without intents, you end up in this like shared
still
global.
need, yes, a bunch of states.
So effectively, I think everyone will eventually have to move to an intent-centric model just to make a bunch of this shit scale and actually work in practice for a bunch of like ZK applications.
I mean, the challenges we discussed, right, is that it's all rosy. You know, you like computed all this, you like going to transition, but somebody like executed this part, and like now you need to go and redo everything, right? So that, I mean, that's always been the challenge with like doing Uniswap like things on UTXO resource model.
Yeah. The nice thing, which I think is underappreciated sometimes, is when you have this very general state model that you can do partial state updates. So you can do like intent I and intent I2 can just transition to I3. They're maybe not yet settable.
Yeah.
But so you can do
So
like this.
recirculate that. Yeah, and then somebody else.
So really like what solvers should optimize for is incremental compute. That like I just keep adding. I don't wait for all the intents that I'm trying to do global search. I'm trying like incrementally solve the intents. And if I sort of after 5 seconds I can't actually solve the rest of them,
then you
I submit it onwards and maybe someone else can. This is also a very nice abstraction actually for like ZK proofs, and if you want to outsource the compute, because you can pick a specific person that you'd like to outsource your compute to, and then that guy just produces the proof. This is, I think, going to be important for constrained devices. Yeah.
All right. Well, it's a lot.
It is a lot. My big recommendation,
read the blog post.
Read Chris's ETH research post. It's like a good hour, 2 hours kind of thing. It's very dense and very long, but it also points to all the underlying. So for better or for worse, we've taken a very principled approach of specs first and research first. So there is, at this point, like 15 different research reports on all these various components, including the cryptography, the networking. It's all on art.anoma.net. If you go to the ETH research post, though, this are backlinks to of the underlying research. Honestly, we should be doing this more often because explaining 15 research papers is kind of difficult. But yeah.
Well, thank you for coming. I mean, this was a good overview for sure. I'll encourage everyone to check out the rest of the research and kind of deep dive, and looking forward to start using this.
Me too. Thank you very much, Ilya.